Alright, so today what I do is start a little section on what are the fields. What are the fields that we play with? And there's actually not that many of them, so we can do them all. So the fields that we do, the ones that we've seen already, and I'll do a little bit more, is the real scalar field. That's what we've been calling phi. Phi of x. Okay, so it has there's no directionality, so it's just a number at each point in space-time. It will end up describing something that's spinless, because otherwise you have to add spin. Okay, if you add spin, it's two numbers at each point in space-time or more. Okay, we go from there, we go to the complex scalar field. Okay, that will also be called phi, but it won't be the same as phi and phi star, not the same thing. This ends up getting used when you describe something that has a charge. So here, there's going to be little wrinkles associated with each of these. This one, there's going to be antiparticles. That's a natural feature of that. If there's some charge. So if they carry some charge, so this would be a particle with, for example, electromagnetic charge. Okay. Then you can do non-relativistic fields. So you can do a boson, or here you can add a fermion. So those things we'll deal with. This is a complex field, because you always describe non-relativistic fields by a wave function, psi star. So when you're doing non-relativistic quantum mechanics, whether it's with spin or without, you use a complex wave function. Okay, then if we do the relativistic version, it's a Dirac field. So this is spin a half. We'll do some of that. And then there's photons, or vector fields. Okay, so the photon clearly is that in the relativistic treatment it carries spin 1. Whereas photons are relativistic. The non-relativistic version of this could be something like a magnetization. So there's a vector, it's a 3 vector. In a magnetization, then it's sort of like a scalar field, except it has a directionality. There are points in some direction. Okay, but the rules all seem to work. And then the last one, which we won't do much, is the gravitational field. But that's it. That's basically all the fields that you'll run into. Non-relativistic versions and relativistic versions of the same old things, same things. Okay. So there's little wrinkles each time you do some of these, like adding spin is a little wrinkle, and antiparticles a wrinkle, and photons have a little wrinkle, which is gauge invariance, etc. Questions? All right. So let's go back and say some more about the real scalar. Okay, it's basically it's anything that has a magnitude phi at x and t, or more generally, we'll just call that phi of x, where if there's no vector sign, it means both x and t. And A good example of this, we did the string. We could also do phonons. They satisfy, they're a scalar density, it's the density. They satisfy a wave equation. So you immediately know what to do. You write down the action is the integral d4x, 1/2 d mu phi, d mu phi. That's saying that is essentially the same as saying the wave equation. And we know how to write out phi here, and we know the Hamiltonian ends up being, the integral d3x, or d3p, 2 pi cubed, h bar, which is 1, omega p, a dagger of p, a of p, plus some 0-point energy, which I promised you I'm going to come back and talk about it, so I will sometime, like just today or tomorrow or next time, but that's it. Okay, so there's a perfectly good real scalar field. Okay, but let's do it a little bit more generally. Okay, there's no reason you have to just write that one out. For example, let's imagine that the Lagrange density starts off like that, 1/2 d mu phi, d mu phi. So that's wave equation stuff. But then we could add things like, let's call it mu squared over 2 phi squared. There's nothing wrong with that as far as any symmetry or anything. You could add, let's call it lambda 3 over 3 phi cubed minus lambda 4 over 4 phi to the 4th plus dot, 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 dot. Okay, there's no particular reason you have to stop at any given order yet. Okay. You could forbid this one by a symmetry. You could by phi goes to minus phi. So let's write that better. It goes to minus phi as a symmetry. That's a symmetry, that's squish. And that depends on the physics that you're after. Sometimes you want to do it, sometimes you don't want to do it. That's driven by the physics. I've put the signs on these things to be negative. Remember, the Lagrangian is the kinetic energy minus the potential energy. So here's a v of phi. The Hamiltonian is stuff plus v of phi. So you tend to put things, when you put a negative sign there, it means it's a positive energy feature, right? So this means that as phi gets big, the energy goes positive up. If I had the opposite sign there and stopped here, then as phi got big, our energy would become arbitrarily negative, and we'd be unstable. So that would be not so great. That's not likely to describe the real world, unless there was a phi to the 6th term here that turned it back up. So, these are things that are driven by the physics in the end, but most often we want the highest power of the field that you include in your Lagrangian to give positive energy, because that way, when the fields get big, the energy goes up. Okay, and that's a nice physics requirement. So the highest power of the energy should be, in terms of the field, should be positive. Otherwise, you have an unstable system. Okay. You'll note. Are you ready for the yes?
What's the dimension of this lambda 3, lambda 4, and 5.
Okay, good. You're the winner of the $1 for the first science question of the day. We need more questions, so that's my little bribe to get questions and pull your fellow into it. Okay, so I want more questions, and good, thank you. It's a good question. So if we're doing dimensional analysis, remember the Lagrangian goes like energy to the fourth power. Derivatives go like energy to the first power because they turn into momentum. And then from this term here, you can read off that phi goes like energy to the first power also. Okay? So in this term here, we have to make up energy to the fourth out of that 2 phi's and mu squared. So mu goes like energy to the first power. And in fact, we're going to see that mu is like a mass. That comes a little down the screen. Okay. This one over here, phi to the fourth already goes like energy to the fourth. So lambda is dimensionless. Okay. And then you can sort of interpolate in between. Lambda 3, so lambda 4 is dimensionless. Lambda 3 goes like energy to the first power. That's a coupling constant. It's dimensionful if you put it in there. It has a dimension. Good. Okay, and relevant for what we do later, so let's just say it now, is that beyond this level here, if we have phi to the fifth, sixth, etc., phi to the sixth is the common one you include, then the coupling constants have to go like 1 over in energy. So they have 1 over energies just to balance it up. Those terms, in the end, when we get there, when we do renormalizable field theories, are all forbidden because they lead to non-renormalizable theories. We're quite a ways away from doing that, but that's one reason why many people doing particle physics type things truncate at phi to the fourth. However, if you're doing condensed matter, there's no reason not to go beyond it because renormalization is not a big issue. We'll talk a lot about that later. Okay, other questions about where we are here? Okay, let's get a little something out. Let's do actually, there was another question that you could ask here. Well, there's no $1 laying on the table, but let's see if someone can come up with what's the other obvious question here. I wrote out phi squared, phi cubed, phi to the fourth. What's missing? Okay. Yeah, so the question is, what happened to the term of order phi? Okay. And the term of order phi, so the question is, why no linear term? You'll never see one. And the answer is the following. If you have a linear term, so let me look at the potential energy as a function of phi. And if I just imagine, here's phi, here's v of phi. If there's a linear term, then right at the origin there's a slope going down. And we know from this argument that we have to eventually have positive energies, that we're going to want this thing to be positive eventually. Okay, so I don't really know the shape of it, but it has to go up eventually. So what you know about anything that has that shape is that there has to be at least one minimum there. And if I go to that minimum and I write phi is phi twiddle plus, let's call it phi minimum, phi at the minimum, then around that point and I just write out the expansion. So around that point, there is no linear term. The phi twiddle starts off as mu squared over 2 phi twiddle squared plus, etc. Okay, you can't get rid of any higher order terms, but you can always get rid of the linear term by just going to that place and redefining it. So you can always redefine the linear term away. That's the answer to that. Okay, so when you see people write out Lagrangians, they don't start with phi, and that's why. Okay? The other thing to be said is that if you started with that and tried to expand around this point, there's an intrinsic instability that's a problem. Okay, so let's do something with this guy. Let's take the equations of motion. Okay, the equations of motion. Remember, we take the variation of the Lagrangian with respect to d mu phi, and you multiply it by d mu phi, minus the variation of the Lagrangian with respect to phi, set that equal to 0. The first term we've worked out already. This term just gives me box phi. That's one we did. The variation of the Lagrangian with respect to phi is, well, let's see if we can get it on the same screen. No, it's not going to work, but it's easy. It's mu squared phi minus lambda minus mu squared phi minus lambda 3 phi squared minus lambda 4 phi to the fourth. Okay. So you plug that in here, so it's box plus mu squared, and I'm going to just take these guys and put them on the other side for the moment. Yes?
That lambda 4 term has a phi cube, right?
Yeah, it has phi cubed there. Thank you, thank you, thank you, thank you. Right. So the equations of motion we end up with are box plus m squared phi equals, on the other side it's then minus lambda 3 phi squared minus lambda 4 phi cubed. Okay. Yes?
That m, the one was a mu above? Or?
Yes, that m is what was a mu above. I'm getting ahead of myself. Mu will turn out to be the mass. Okay, so this breaks up into two parts. Here's a modified wave equation. Okay, so it's really the Klein-Gordon equation. Derivation plus mu squared phi. And these terms over here are going to be treated as interactions. We actually won't be using the equations of motion. In doing that, we'll use a time development operator. But that's what these guys are. These are nonlinear interactions. And in the end, there's something that goes like phi to the fourth up there, the lambda 4 over 4 phi to the fourth, is going to end up implying four-particle interactions, scattering processes, for example, among other things. But sometimes you do use the equations of motion. You'll get a homework problem soon doing that. Okay, so the lowest order, the free field, with no interactions, So free field means no interactions. Is D'Alembert plus m squared phi is equal to 0. Mu squared. Thank you. I'll learn my lesson eventually. Okay, mu squared phi is equal to 0. And it's easy to solve solutions. Well, the typical solutions we look for look like plane waves, e to the minus I et minus p dot x. The equations of motion then turn into minus e squared plus p vector squared plus mu squared equals 0. So it tells us that the energy squared is p vector squared plus mu squared. And that's the relativistic energy momentum relation where mu is the rest mass. Okay, and again with c's in there, there'd be p squared c squared and mu squared c to the fourth, but we've cleaned up all that stuff up. Okay, so there's a more general version. Questions about it? Okay. So here's some hand waving, but it's not hand waving, it's really true. But why are strings and phonons massless? In other words, why do they satisfy box phi versus box plus mu squared phi? Okay. And there's a physics reason for this. And the easiest way to see it is to go back to see how we constructed them. So let's go back to the string. So and I'm going to argue for is what we'll call a shift symmetry. Okay. So the V we originally started was with the coordinates y, how big they oscillated, but those were really V of yi plus 1 minus yi. Okay. Okay. So there's no energy cost if you take yi goes to yi plus a constant, you shift it for all I. Okay, so if you do it for all of them, you just shift it by a little bit, then the potential energy stays exactly the same. Okay, but then if we then construct a Lagrangian, then you go to a field. That will turn into y turned into phi. That says that there's a symmetry phi goes to phi plus a constant. That's a symmetry of that theory, and that implies that the Lagrangian, if you try to write out stuff that has mu squared over 2 phi squared in it, that thing's forbidden. Okay. So this symmetry there tells us ahead of time that we're not going to have phi squared. So you don't actually write that. You wouldn't even try writing down. You could even just write the answer out. You know it. And the same thing actually holds true for phonons. Phonons, it's a little harder. remember phonons, what the physics of it is it's the atoms in, let's say, the gas compressing a little bit, so the density is bigger here than it is over here. Now, if you think of that as a wave, we've got this big wave. Well, first of all, for small waves, it's compressed here, it's compressed here, it's compressed here. But as the wavelength gets very large, this wave moving along is just sort of like shifting the whole system. You know, as lambda goes to infinity, you're basically, you know, you're sitting here, the compression is going on over that whole distance here. I'm pushing a little on the atoms here, but the atoms next to it are also moving. Everything's compressing sort of uniformly as the wavelength goes to infinity. And so you really, as lambda goes to infinity, the wavelength goes to infinity, there's no energy cost. Okay, for a phonon. So that's basically the logic, you know. So as the scale becomes very large, you can say that the energy should go like the wave number. So omega goes to 0 as k goes to 0. And once you make that logic, you have only one of two choices. If it goes like k, that's fine. So this is the general shift symmetry logic. You could get energy going like k. The only complication in this argument is that it could go like k squared over 2m, you know, if you wanted to. But that's also consistent with the shift symmetry. But in the phonon case, it's not. This is the wave equation. So it's basically the nature of your dispersion relation at low energies tells you whether you add that mass term or not. Okay, so the mass term is a energy cost for having a field around. Okay, it ends up being quantized, of course, but that's... Now, when would you not have this case? So let's take a simple field theory with a mass term. Okay, let's imagine that instead of doing the springs, I made it a little harder qualifier problem. Okay, so we put the springs on the bottom of pendulums. So here's the ceiling, and we have a bunch of pendulums hanging down. Okay, and we connect these guys with springs. Okay. Now, our logic tells us actually that that's going to turn into a field theory, but it's going to be a field theory that satisfies the Klein-Gordon equation. And here's the reasoning why. So here, the displacement would be the displacement in the angles or the radial direction. There you could use theta, or r theta, if you want something that actually has the dimensions of a coordinate as your variables. So those are the things that are going to turn into phi. The spring energy, of course, still has the springs goes like the difference is 1/2 k. It's r theta I plus 1 minus r theta I squared. That's how far apart. That's how far you've stretched the spring. But now I'm also now, since these are pendulums, hanging in a gravitational field, so there's a gravity. It's m gr cosine theta, which if I expand that goes like m g, well, r theta squared over 2. Actually, I want that guy squared. There. That's what it looks like if I expand that. So if r theta turns into a field phi, this guy has the shift symmetry, but this guy doesn't. This one, if I have any excitation, if I excite them all together, there's still some energy. So this is going to turn into a phi squared piece, and the coefficient of that we call mu squared over 2. And so if you just do the same old calculation as we did before, you'll get a mu squared phi squared piece out of that. And if you form the continuum, you're going to find box plus mu squared phi equals 0 instead of the usual wave equation. Okay? So after a while you get your intuition up, and you know that this thing is going to give you a mass term. It also gives you a phi to the fourth term also, right? So there's also going to be phi to the fourth terms. And yes?
So the major difference between the gravity term and the spring term, because they're all quadratic in theta?
Yes, they're quadratic in theta, but one depends on the difference between theta 1 and theta 2. So if it was just the springs, and I rotated them all together, there'd be no cost in energy. So without gravity, there'd be no cost for having this long wavelength solution where you just rotate everything together. But with gravity, there is an energy cost. So once you get to the energy, you have to know that if I take these things to be non-zero, even if there's no kinetic energy flowing down this thing, there's still some energy cost. So the Hamiltonian that you're going to want from your theory, your Hamiltonian, is going to have kinetic energy pieces that depend on gradients, and then it's going to have a mu squared phi squared, and there'll also be a lambda phi to the fourth, which is also, okay, things like that. And it's just, you know that just because there has to be some energy cost if you make these things all go together, even if there's no gradients around. Whereas for the phonons or for the strings, all the energy is contained in the gradient. If you shift everything by a constant, nothing happens. Okay. So there's an attempt to get a little intuition there on that.
So we say waves in that setup have something like a mass.
So they would have something like a mass, yes. Right.
Can we imagine that?
What?
How can we imagine that? Because
Well,
they don't fall down on the floor.
no, they don't fall down on the floor, but they don't propagate. If you turned off gravity, the waves would propagate with some speed. They actually propagate slower than that speed than with gravity. Gravity ends up having to retard them in some ways. It makes it go slower. Just because there's some, well, yeah, that's, so it's not the springs that are the masses. I mean, they do have masses. Each of these has a little mass point. But it's the wave itself that carries this extra term here. Now, you're probably not going to interpret it as a fundamental mass in this, but it has the same dispersion relation as a piece with a mass. So in fact, you can actually take, well, so that's, if I did that, then I end up with E squared is P squared plus mu squared, just a second. And then for the lowest energy states, then it ends up then for very low energy states, it looks like mu plus P squared over 2 mu plus da da da. So that's the type of thing you get that type of dispersion relation. Somebody had a question. Yes, for you.
Pi will be again 1 over v squared.
Yeah.
Pi over dt.
Right. Yes. Yes. So pi. So buried in this thing is actually the v instead of c. V being the velocity of sound due to the spring system. So, but this then for large wave numbers is the dispersion relation you get out of this guy. Okay. Okay. So many times actually, if you're doing this thing at very low energies, you might just do a non-relativistic reduction of this. So really, this is wave equation plus mu squared. It looks like formally like a relativistic theory, but if you make this non-relativistic, you end up with something that looks like a non-relativistic theory with a mass mu. I don't know much else to say. If you want to have a little exercise, if you have some time on your hands, you want to try doing it, you could just try putting all the factors in there. I did all the factors for this problem at the start of the course. We could do this and see what determines what mu is. It's mg times something. I actually haven't done it recently. You can figure out what determines these coefficients here in the continuum limit, if you want. I was thinking of making that a homework assignment, but I have one that I think is more fun. So we'll do the more fun one. Okay. Questions on that? Okay. Before going on, I just want to write out the quantization. Just because I don't think I've written this out since we dropped h bars and c's. Okay, so this is what it looks like with h bars and c's disappeared. Okay, so phi of x and t is integral d3p over 2 pi cubed, so there's no longer an h bar there. There's a normalization factor, which is 1 over the square root of 2 omega p. And then there's e to the minus I p dot x a of p plus e to the plus I p dot x a dagger of p. Okay, so that's now, we've cleaned up things. There used to be some h bars and c's in here, and there's p dot x over h bars. So there's the things you look at. What you follow when you see this. Well, unfortunately, we have to follow this normalization occasionally. It actually is going to play a role in what we're just about to do. The creation, the annihilation and creation operators, and then the plane wave states. Remember, when you see p dot x without a vector sign on it, that means e to the minus I et minus p vector dot x. So that's also compacted its notation. Does everybody see what's in there? Okay, so what I want to tell you about next is something that's going to play a big role in what we're doing. We're just going to construct it without knowing its role yet. I'll tell you after it's constructed how it gets used. And that's the Feynman propagator. Okay. It's going to get used everywhere later. It's a Green's function. Its definition is I df. Df is a symbol for the Feynman propagator. X minus x prime. It has two variables. And x and t are contained in that. So it's a function of x and t, x prime and t prime. Okay. It's defined as time-ordered product of phi of x and t phi of x prime t prime taken between these ground states. Okay. Let's just talk first about the symbol t. T is the time ordering. And it basically says early is on the right. Okay. So anytime you see it, you could see it with 4 fields, 6 fields, whatever you need. And we get it later. But the earliest is always on the right, and then it's ordered according to time. Okay? So, but we don't, we're not making an assumption about whether t is greater than or less than t prime. So here's explicitly what it is. Time ordered phi of x prime, or of x, well, it doesn't matter, x, phi of x prime is, well, it's theta, the theta function, the step function, t minus t prime, phi of x prime, plus the other ordering, theta of t prime minus t, phi of x prime, phi of x. Okay? So this says that if t is bigger than t prime, then the bigger one sits over here, the earlier one sits over there. But if t prime is bigger than t, the later one sits over here, the early one sits over here. Okay, that's the general definition of time ordering. Okay? And the reason this enters into quantum mechanics comes from the convention that we write our initial states over on this side, on the right side, and our final states over here, and things happen causally. So that as you're propagating from early times to late times, things happen on that state. So phi's are going to create or annihilate particles, for example. But the causality requires that if you create a particle with one and annihilate it with another, the creation always happens before the annihilation. Okay, you can't annihilate something that's not been created yet. So this time ordering follows from the convention that early states are over here, final states are over there in quantum mechanics. And that's where it's going to enter, is when we do interactions, we're going to write a time development operator that takes your initial state, ends up at your final state, and naturally that comes out with time ordering in it. Yes?
Well, you want to do a relativistic theory there.
Yeah.
Could be quantum.
Yes, good question. Great question.
There
It's,
is no
yes, yes. So the question is a great question, because you know that in relativity, this question of which thing occurred first is a relative statement if you're moving with respect to some frame or not. The amazing thing, and this is not something I can just prove to you by words, is that it ends up, even with this time ordering, always being a relativistic invariant. And we'll actually see that today. We're gonna write a expression for this thing one way that looks like it's not relativistic invariant, and then we're going to work a little harder by doing Fourier transforms and putting I epsilons in the right places. And the final answer is going to look relativistic invariant. And as far as we're all concerned at this stage in class, that's a miracle. But it's a great question, and the answer is let's just hold on, and we'll see the relativistic invariant answers come out. And formal field theorists will prove that for us at some stage. Okay, but it's certainly not a given at this stage. But this, you'll see it. You'll see this one today. This one will come out in a form that is obviously relativistic invariant before the end of the day. Okay, so that's the beast. Well, we can calculate it. It turns out it's a Green's function. So maybe I should show you that it's a Green's function first. Okay, what I mean by it's a Green's function is that if I take D'Alembert respect to x plus m squared, I'll use m here rather than mu, times I df of x minus x prime, it's going to be equal to minus I delta 4 of x minus x prime. Okay, so if you remember your Green's functions from E and M, that's the typical thing. You take wave equation on this beast, it gives you a delta function, either 3-dimensional or 4-dimensional, depending what you're doing. Okay? Okay. This is true if the field satisfies box plus m squared phi of x equals 0. Okay. Okay, and then to do this, all right, so let's just go up here and just look at the strategy first. Again, think back on Green's functions for you. One of the things that we have here is there's some discontinuity at t is equal to t prime. The ordering of these things shifts. And so when we act with box plus m squared, there's going to be a couple things that happen. It could be that all the derivatives here in the D'Alembertian act on phi. So there's phi of x. This is derivatives with respect to x. If all the derivatives act on that phi there, so d by dt and d by dx, then I'm going to get 0, because here's my equation. So if all the derivatives act on that, that gives me 0. However, time derivatives can be different. Spatial derivatives, that's all they can do. That's the only place spatial x enters. Time derivatives can also enter onto the theta functions here. And remember, the derivative of a theta function is a delta function. So we're going to get some time derivatives acting on these guys. And that's what I'm going to work out first, is what happens when I take time derivatives on it. And we'll see there'll be a couple things with time derivatives on the theta functions, times some stuff on phi. And then the last term will be everything on the phi. Okay? And the everything on the phi is going to combine up with spatial derivatives to give 0. Okay, so all the action happens on the time derivatives. Okay? So, let's do it. So what I'd like to do first is just look at d by dt squared on time-ordered product of phi of x and t, phi of x prime, t prime. Okay, and I'm going to do it one derivative at a time. So I'll keep one d by dt out in front for the moment. And I'm going to act with that first one. Okay, so there's my time-ordered product sitting up there on the top. And so the first thing, let's do it is, if I just have it act on the phi of x and not on the theta functions, then I just get time-ordered product of phi dot with phi. Okay. So the first term in this thing would be time-ordered product d by dt of phi times phi of x prime. That guy's at x. Okay, and that's going to be the boring piece. Okay, so it hasn't upset the time ordering. It's whichever one it is. Okay, then the interesting piece is there's two terms. Is when I act on the theta function, I get a delta function. Okay, so doing that, let's do that. I get on the first term, I get delta of t prime minus, or t minus t prime, sorry, times phi of x prime. And the other one, I get, so in the one case, the derivative by t steps up as I go past t prime. In the other case, it steps down. It's 1 when t is smaller, then it goes to 0. So this guy picks up a minus sign. It's minus delta of t minus t prime. Phi of x prime, phi of x. Okay, so out of that, guys, so that's all I get there. Out of that, I get a delta of t minus t prime. Delta functions, the time ordering the order doesn't matter. And I get the commutator of phi of x with phi of x prime, which is 0. That's one of our commutation rules. So the first time I took a time derivative, I only get this guy. Okay. You comfortable there? Ready to go on? Take another one? Here's where all the excitement comes. This is okay. So I do the same thing again. The second time I do it, I put the time derivative. If I act on the field, it's d squared t squared phi of x prime, time ordered, so there's nothing there. But again, now I can differentiate the time ordering, and I get plus delta of t minus t prime. I get these two terms again, just for the time differences. But now instead of 2 phi's, I get d by dt of phi and phi. Aha, but that's going to be canonical momentum in phi. So this thing turns into, it's the commutator of d by dt of phi of x and t with phi of x prime, t prime. Okay. So instead of the commutator of 2 phi's, now I've started with 1 d by dt and 1 not. Okay. Well, and here again, the subject hangs together remarkably well. This delta function says that these two times are the same, so t prime equals t, right? And this then turns into the commutator of pi of x t with phi of x prime t, the equal time commutator, which is it's minus I delta 3 of x minus x prime, so it's just the 3 stuff, but that's all you need at this stage, right? It's a minus I because really the commutator is phi with pi is plus I, so this is pi with phi the way it came out, so it's minus I. And so the answer comes out then minus I delta 4 of x minus x prime. So t is already there. Here's d3x. And then the rest of this stuff will be I'll call normal terms. Which end up turning into, in the end, when I do the space derivatives also, box plus m squared on phi, which is going to be equal to 0. Okay, so the d by dt squared that sits here, there'll be spatial plus spatial derivatives, or minus spatial derivatives squared, plus m squared. That gives you this equation, which is equal to 0, so the normal terms end up vanishing. But I got my Green's function out there. So we can do with this what we do in E&M. It's basically a Green's function that lets us tell what the reaction is in the end to something happening. So we're here, we'll be coming along, and in the end, we'll be coming along, we'll be propagating along our initial state. Something will happen. This thing will be a Green's function. It'll tell us how the disturbance propagates from here to there. And that's how we end up using this guy in the end. Okay? So, what I'd like to do now is calculate it. Okay, I'm going to do two calculations. So let's solve for it. But actually, anyone want to ask a question about that? Okay, so there's it's satisfied.
Small question.
Sure.
Is this the Green function for the operator box plus m over box plus m squared?
Yes. Yes, it's the Green's function for that wave equation. Yes, exactly. Right. So there's the definition of this Green's function. And aside from a little bit of I-epsilon physics, which we have to explain carefully, which is more subtle, if I just set this m to 0, it's the Green's function that you see in E&M connected with radiation. Okay, so if I put the I-epsilon in the right place, it's the retarded Green's function for radiation in E&M. So I put m equals to 0, and I put an I-epsilon in the right place. It's something that you've seen in E&M. Now I'm going to put the I-epsilon in a different place, which is always fun to explain. Okay, so let's solve it in terms of solutions. So it's a representation in terms of solutions. Okay. Well, we have this expression for phi in terms of creation and annihilation operators, and we know what happens. So let me just put it in here. Phi IDF, x minus x prime, is 0, this empty state, time ordered. Well, phi is integral d3p over 2 pi cubed, 1 over the square root of 2 omega p. A of p e to the minus I p dot x plus a dagger of p e to the plus I p dot x. And then the other one, so that's phi, and here's phi prime. My integration variable will be p prime, 2 pi cubed, 1 over sort of 2 omega prime. Same thing, a of p e to the minus I p dot x plus primes all over the place there, p prime e to the plus I p prime dot x prime. 0. Okay. Now, we know what happens when, let's for the moment take this ordering as the right ordering. So t is bigger than t prime. So this is the early guy, this is the late guy. Okay? Well, we know that when A acts on this empty state, it gives 0. It's an annihilation operator. There's nothing to annihilate. When A dagger acts on it, it creates a particle. And then over here, this guy will annihilate that particle and turn it back to the empty state. So the interesting piece here in this ordering is this guy creating something, this guy annihilating it, coming back to the ground state. Okay? Fair enough on that? Okay. So we're going to use A of P on this thing is 0, on the empty state is 0. And if we have something that looks like A of P, a dagger of P prime, 0. Well, again, the way you do it formally is you say this is a of p commuted with a dagger of p prime plus the reverse order, a dagger of p prime, a of p, right? This guy gives 0, because a acting on that state gives 0. This gives me 2 pi cubed is the normalization convention. I use delta 3 of p minus p prime. So that gets rid of one of the p prime integrations. I'll have a p integration left over, and it looks like the following then. So I df of x minus x prime is, well, there'll always be an integral d3p over 2 pi cubed. There'll be a 1 over 2 omega p. Okay, that comes from the two square roots. P and p prime are the same, so those are the same, so it's 1 over 2 omega p. And now there's a time ordering issue. The one we just worked out is theta of t minus t prime. So when t is bigger than t prime, we just worked that out. Then we had e to the minus ip there, and e to the plus ip prime here. That was associated with the a dagger. So is e to the minus I p minus p prime dot x. That's what we just worked out. In the reverse, the other time ordering is just everything reversed. Is theta of t prime minus t e to the, well, let's write it as plus I p minus p prime dot x. Okay, so it's just the reverse of the other one. Okay, so there's the answer. Okay, comfortable? All right. So there's one solution. This is the one that looks non-covariant. This certainly doesn't look relativistically invariant at all. Yeah, this part here, e to the ip dot x, that looks like it could be relativistic invariant. But here I've got a bunch of terms that don't look like they're the same in everybody's frame. Okay. So, of course, I'm going to solve it another way now. So now I'm going to solve it by Fourier transform. Okay. Actually, it's an interesting exercise if taking the wave equation on this, showing that it gives you the delta 4. But again, it comes from the delta t comes from this guy, and the delta 3 comes from these e to the p dot x pieces. But yeah, since we have two time derivatives, it's a little bit tricky. You have to, one of the time derivatives kills the 2 omega, and you're left over the delta function. So again, it could be an interesting exercise to just take box plus m squared on that and show that you give a delta function. But in some ways, I'm going to prove it the roundabout way. I'm going to solve it by Fourier transform and then show that the Fourier transform, when done right, gives exactly that formula. So I'm proving it a different way. Okay. So here's how you solve it by Fourier transform. Okay. I want IDF of x minus x prime. I'm going to Fourier transform all the variables. So it's integral d4, let me call it d4q, 2 pi to the 4th, I'll put it as a convention, e to the minus I q dot x minus x prime. Some d of q. Okay, so I've got some function. I want it to be a Green's function. I've got that as my ansatz. Okay. Yeah, you can Fourier transform any function, so this is a good one to Fourier transform to do. So now if I take box plus m squared, so derivative with respect to x plus m squared on I df. Okay, well, it goes right through the d4q, pi to the fourth. Well, when I take d by dt, it brings down q0, whatever q0. So remember, there's q0 and q vector. So maybe for once I'll just write out all the components there. This turns into minus q0 squared plus q vector squared plus m squared times the exponential back again times df of q. And once I'm comfortable that everybody is fluent in relativistic notation, I would just call that minus q squared plus m squared. So that's what I'll do now. You know, no vector sign on it, so it's a 4 vector. Q0 squared minus m squared is the Lorentz 4 vector, which is, you know, it's minus q mu plus m squared. So, okay, everyone comfortable with that? Yeah, now that I've said it. Okay, well, we have to have this equal to minus I delta 4 of x minus x prime, but we sure know our Fourier representation for that. It's minus I integral d4q, 2 pi to the fourth, e to the minus I q dot x minus x prime. Again, all 4 of those guys are up there. So that's a 4-dimensional delta function in time and delta function in space. So at this stage, it doesn't take a rocket scientist to tell me that I df is I over q squared minus m squared. Okay, so there's our Fourier representation of this. Again, if I was doing the exact same thing for photons back in E&M days, I would just cover up the m squared, and I'd get that. In the convention in E&M tends to put 4 pi's floating around here, but we're better than that. We don't need those bloody 4 pi's. So it tends to go like that. Okay. So that's the answer in some level. Now, and so this one partially answers this relativistic question. This guy sure looks relativistic. This is a relativistic invariant. Q squared is, you know, the relativistic form q0 squared minus q vector squared, and that's relativistic invariant. So it looks like we're relativistic invariant at this stage. It's not a, well, it is a big deal, yes. However, I have to do something next that there's no way I should attempt to start this now. This guy is actually slightly ill-defined here because there's a pole here. So I'm supposed to integrate over all q's, positives and negatives, and q0 and q vector are treated separately here. They're not related at all. We're integrating over all of them. That's what the integration tells us to do. So this takes all values positive and negative when we do that. In particular, it takes a value, it goes through the value when q squared equals m squared, and there's a pole sitting here in this little integration. So it's a little ill-defined there. So what I need to do is I need to make this better defined. I'm going to do that by putting I epsilon in. And I'm going to stick an I epsilon in there with the intent to make it equal to that formula above. Okay? This way we've got from solid ground. And so when I put my I epsilon in there, I'm going to show you that when I stick it in the right place, I get this formula out. Okay? That has to be the task to start off next time, because it's inherently confusing, but we'll try to do it slow enough so we can tell you why it equals this way and why it's not done elsewhere otherwise. Okay? Good. Well, see you on Thursday then. See you on Tuesday. Sure.
I didn't follow, actually, this line we have here, when you go from this line to this line,
Yep.
this delta 3, what it does is...
Yep. Yes, it's a del. Yes, so it kills.
To understand, the only two contributions are when this one falls through,
Yep.
but this one gives you a delta.
Yes.
So you have two integrations, so this delta kills one of the
Right.
integrations.
Exactly.
And then I end up having one integral,
Right.
and the propagator has these theta functions there.
That's right. So the theta that thing has been turned into those two theta functions. The two square roots is turned into one factor.
So okay, so when you have the time ordering operator, what you do is take the sum of...
Yeah, you do one time order and then you do the other, and you write it with these theta functions.
Okay, perfect.
Okay.
Good. Thank
Good.
you.